Good evening all, and welcome to tonight's TI webinar hosted by Texas Instruments Australia. We are really excited to bring you coding in the Victorian 7 to 10 curriculum with Frank Moyer and David Tynan. My name is John Bayman and I am your host for this event. I teach mathematics to year 7 to 12 students at O'Loughlin Catholic College, Darwin, where I use TI technology to help students make stronger connections in their understanding of mathematics. I'm excited to introduce our first panelist for this evening, Mr. Frank Moyer. Frank has vast experience in teaching mathematics, curriculum development and sharing his knowledge at national and international conferences. Frank is also passionate about rich tasks and the use of CAS to strengthen and deepen students' and teachers' understanding of various mathematical concepts. Frank, thank you for being with us this evening.
Thank you.
Our second panelist is Mr. David Tynan. I know that David has a keen interest in the role and impact of technology in the secondary mathematics classroom, and I'm looking forward to him sharing his knowledge and skills with us tonight. David, thank you very much for joining us.
You're very welcome.
So I'm going to pass over to Frank.
Okay, thank you. For my part of the webinar, what I'll be doing is talking about what's in the algorithms and coding part of the Victorian curriculum, and then I'm going to be looking at an activity called nested square roots. This activity will involve coding a recursive algorithm. So the algorithm code will include using loops, using set structures, and I'll talk a bit about what I mean by set structures, and decision making. And then after that, I'll hand over to David, who's got some more examples to have a look at. Can you see my desktop as yes?
Yep.
So we're all
very well organised too. Thank you, Frank.
Okay.
I can see it fine. Thank you.
All right. So unpacking the requirements in the Victorian curriculum. Well, first of all, in the previous Victorian F to 10 curriculum, it was really just an implementation of the ACARA Australian curriculum. But in the new 2017 mathematics curriculum for Victoria, there is a subtle but very important difference, I think, and that is that in the number and algebra part of the course, at every year level, there is a requirement to include algorithms and coding. So why include algorithms and coding? Well, as far as I'm concerned, these are vital 21st century skills, and I think that they fit naturally into the mathematical proficiencies of reasoning and problem solving. So I think that we can and should be embedding this material into our maths. It's not something that we should just handball to the IT teachers. Just as we have literacy across the curriculum, I think that like some other countries, we need to be moving towards coding across the curriculum. Now, it seems to me that the focus of this new material is on algorithmic thinking, and there are, I think, three key elements. Sequencing, so having an ordered sequence of commands. Decision making, so things like using if statements in programs, and repetition, the use of loops. So the new material is probably best implemented by including it into existing topics. I don't see it as a separate standalone topic that we do sort of at the end of the year or whatever. I think it's something to include throughout the course. So let's have a look at the specific requirements. Can you see my screen for level 7, yes?
I certainly can. It's wonderful, mate.
Are we on level 7 yet on my screen?
Yes, we are.
Oh, okay, good. Okay, I'm just not sure how quickly it's moving through. My internet connection has been very slow all day. Okay, so this is what it actually says. So this is the content description, which is a required material. So design and implement mathematical algorithms using a simple general purpose programming language. So here it specifically mentions the word algorithm and the word programming. Now, the elaboration, which are advisory and optional, give an indication of the sorts of things that you might do. So the first elaboration is finding the sum of a set of consecutive numbers using a loop structure. So here, the concept of repetition. So students should be writing algorithms and simple programs using loop structures. And the second one is interesting, constructing geometric patterns such as honeycomb using dynamic geometry functionality. So I think what this is alluding to is the idea of recursive geometry. I think recursive art and recursive geometry are the sorts of things that, say, people who design video games would need to be coding. Year 8, it's less clear-cut as to what students need to do. The content description is, use algorithms and related testing procedures to identify and correct errors. And the elaborations, debugging search and sort programs and testing a number for divisibility. Now, from that, it looks as though all students are going to be doing is debugging, but I don't think that's the intent. I think the intent is that in addition to developing and analysing, by year 8, students should also be looking to validate algorithms and programs and use test cases to see that the program works as it should in all cases. So, for example, how does the program respond if a user enters a negative square root? Can it handle that? And how would you fix it? So I think it's doing the same sort of thing as year 7, but going one step further and trying to validate. Okay, so year 9, apply set structures to solve real-world problems. Now here, it's not even obvious that it's about algorithms and coding. Because what are set structures? Well, I think that the elaborations give it a clue. Using a sort algorithm to determine the median of a set of numbers and exploring variations in proportions. So what are set structures? So a set structure uses things that work on a set, which in the case of Nspire, a set is just a list of elements. So things like cardinality, counting the number of elements in a list, selecting particular elements. So if you have a list called sample, if you input sample and in square brackets n, it will select the nth, sorry, not n, but n, where n is a number, it will select the nth term. Impose order, so using things like sorting algorithms. Break up or combine, so things like the Augment Command. So to illustrate that, I've got some lists. So if I have count, list 1, it will count the number of elements in list 1. So that's the cardinality, 25. If I include comma list 2, it counts the total in list 1 and list 2. Augment, if I have the set x, x is just a number, but if I put that in curly brackets, then it now becomes a list. So it's now x and list 2. I've augmented them, so I've now joined them together. Now that's something which I'll be looking at in the example that I'll be going through. List 1 in square brackets 2, it will now select the second element. The second element in the list is the number 1. If I change that to 4, then it returns 2 because 2 is the 4th element, and so on. So they're the sorts of things that set structures refer to. Year 10, implement algorithms using data structures in a general purpose programming language. So the example is the use of matrices and the use of pointers. Pointers are just commands that point to a particular location. So things used like using a go-to command, I think is what they mean by pointers. All right, so what are data structures? I think data structures refers to things that are a bit more general than set structures. So to include not just lists, but also things like matrices and things like predefined objects for storing and organizing data, things like using sort ascending, sort descending, sum, delete void, mean, max. So all of those sorts of things that work on a data set, I think, is what is meant by set structures. Sorry, data structures. And 10A, devise and use algorithms and simulations to solve mathematical problems. And I think that that's fairly self-explanatory. The examples I give is designing a systematic guess, check, refine algorithm and using simulations. Okay, now if you're new to coding with TI-Nspire, these are the resources that I suggest you look at first. First of all, go to the TI Australia website. These TI codes, click on that. That takes you through the basics. In Australian Curriculum Nspire, under the heading of STEM, there are already a number of activities there ready to use. There's, of course, webinars, not just this webinar. There have been past webinars on coding, which are all relevant to the Victorian curriculum, and no doubt there'll be others in the future. The TI-Nspire Program e-guide I find quite useful. If there's something I'm not sure how a particular command works, so I go to that. There's another site called TI Basic Developer, worth looking at. And the textbooks, I only had a look at a couple of them. Pearson has activities, coding and algorithm activities scattered throughout the book. Cambridge has a chapter at the end, which doesn't necessarily mean that it should all be done together. It's something that you can dip into as needed. And this file, by the way, will be available after the webinar. You'll get a link to this file so that you'll be able to get those websites. Okay, so I'm now going to have a look at a specific example. So the example I'm going to have a look at is nested square roots, which involves coding using loops and set structures. So what we're going to do is explore sequences of decimal approximations for nested square roots. And nested square roots are square roots that contain, that is, they nest, another square root expression. So I've got an example there. So you've got the square root of 5. That's the initial value in the sequence. The next value in the sequence nests the previous one. That's why I've used color coding to illustrate that. And so it's recursive. The next term just nests the previous term. And I must mention Carol Moll from South Australia, who introduced me to this problem many, many years ago, long before I'd done any coding.
That's a nice use of colour there, Frank, isn't it, to show where one square root fits inside the other?
Absolutely, absolutely. And I think that that's the key. Students realising, I think for students to understand the recursion, I think it's very difficult without the colour. Okay, so before doing any coding, this is I first of all start with the calculator application, and so that students really understand the algorithm and the recursive nature of it. So first of all, I'm going to add a calculator page. I'm going to initialize that input. So I'm going to, actually I'll do it as though I was, even though I'm in computer view, I'll do it as though I was using the handheld. So I'm going to insert a calculator. So I write the initial term, so the square root of 2. Now, because I want an approximation, what I want is a sequence of approximations, so I'm going to put a decimal point so that I get an approximation. And now what I'm going to do is I'm going to nest that inside the square root of 2 plus and the previous answer. So to get answer, it's just control and the negative sign on the handheld, and just press enter. And we can see that what it's done is it's nested the previous answer inside the square root. And every time I hit enter, whoops, try again. What happened there? I messed it up.
I think you were highlighted up above when you did it. You were in the answer.
Okay, so I'll get rid of this and that. Okay. Good heaven. Because I was highlighting it, I've messed it up. Okay, let's start again. Okay, so got square root of 2, square root of 2 plus answer, enter, 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 without highlighting anything. That's what I did wrong before, so it was just copying and pasting what I'd done previously. And we can see that it is nesting the previous value, and we can see that it's also approaching or converging towards an integer value too. So what is the next value? What is the next value that I could have had that when I nest gives me an integer value? That's what we're going to explore. Okay, so we're going to write a program to help us where we're going to do exactly the same thing. So what we're going to do is get a sequence of approximations for any value A. So the user can input the value of A. So what we need to do is get a program editor. We then need to define and initialize variables. Then the next step is write a recursive loop for the algorithm, and then results and cleanup. So let's try doing this. Actually, I'm running it a bit short of time, so I might just illustrate how you would do this, but I'll use one.
Take as long as you need, Frank.
Okay, not a problem. So to get the editor, it's like inserting any other type of page. So Control I or Control Doc, and I want Add Program Editor New. So you can now give that a name. So I'll call that Nested. In fact, Nested 1, because we're going to start with the basic program and then get increasingly more sophisticated. Okay, so it's set it up for us. So we've defined Nested 1 program. Now, what we had to do first was to initialize. So request, we want to request the value of A. Then we want to initialize. So xn is what I'm going to call my first decimal approximate, or the nth decimal approximation is going to be xn, so I need to initialize as the approximate value of root A, and then I set up the loop structure. So request, so menu, because I'm in I'll move back to handheld view because I want to do this as a student would do it. So menu, and it's under input output. So I want to input, I want to request, and if you want text to appear, you need to put that in inverted commas, A equals, whoops, and then comma to separate that, and A.
Frank, I think it's quite important as well it's easy when with teachers using the software to forget that the kids are using the handhelds in the main, and that, like I said, it's important to go to that view so they can actually see what's actually happening, the buttons you're pressing.
Yeah, that's right. I mean, it looks a bit clumsy for a presentation. However, I thought probably best to do it as a student would do it.
That's right.
So The next one was initialize, so xn, so we're going to have xn, my initial value, so I'm going to assign that. So it's the dot dot equals, that's a sign, the same as define. I could have, instead of just had define, is the square root of a. And a, we'll know what a is when we've actually set that up. Okay, now I want to set up a loop. So loop is under control and for end for. So I want to do this 10 times. So I'm going to come up with a variable which I'm going to call k. Some books show I. I don't like I because later on when we're doing complex numbers, I has a different meaning. So k, and this is where I'm going to jump ahead. We can get really fancy and say that I want to make this a local variable. It doesn't, it has no meaning. So I could even make that, I'll get fancy right at the outset. Define variable, I can define that as a local variable. So k is local, so it exists nowhere other than in the program. Now I need to initialize, sorry, I've already initialized the value. Now the algorithm is the square root of a plus my value of xn. Now, so what I've done is I've captured the current value of xn, and what I want to do in the algorithm, and I want to store that as my new value of xn. So this is where the looping comes in. And the other thing I want to do is each time I want that value of xn, the current value of xn, to be displayed. But I also wanted my initial one displayed, so I'd better put that early on. So I want to display, so menu, under input output, display xn, and end for, so that's the loop finished. And if I wanted to get really fancy, any variables I didn't want at the end, I can delete. So I can go under under actions, I think. No, somewhere you can, but it does allow you to delete variables. Okay, so I'll just type it in. And I could delete the A, for example, when I'd finished, and the xn, so that next time I run the program, it's not going to be an issue. Okay, and the last thing I need to do is to store that, to check and store. Now, I may have made an error, so let's see whether at least the syntax is correct. And it says stored successfully, so the syntax was, it doesn't mean that it's right, it just means that the syntax was not an issue. Okay, now I can run that in a calculator application, so I insert calculator, and if I now go to variable, nested one, now this nested SRT one, that's one I prepared earlier, so that if I messed it up live, I had another one to fall back on. Okay, so this is what's happening. As soon as I run that, I'm prompted to put that value in, so I might write my value 2, and it didn't work as I intended. And why not? Because, of course, I need approximations. So what I needed to do was put in approximate. Okay, now I've frozen, have I? Okay.
It's not changing on this end here, Frank.
Here we go. here we go. Because I forgot to put in approximate, it's taking a long time to work its way through. Okay, so what I should have done is put approximate, because what I need is an approximate number. So that's one of the hazards of trying to do it live. All right, and okay, so this is the one I prepared earlier. Let's try it again. Okay, it worked like clockwork. All right, so this time it is because I had approximate value. All right, so I should have put approximate square root of A. And just very quickly, I can then develop that further, so that what I want to do is generate that in a list instead of showing it the way it was. So you'll get this, you'll be able to download this file. So this time it's going to display it a little bit differently. So I've just changed that slightly so that when I run the program, it displays it all in a list, which means that if I then link that list, which I've called XN list, and put it in a spreadsheet, I can see the values in a spreadsheet. Now, I've then made a slight adjustment so that this time, instead of just inputting one value, I can input a range of values. So I've shown you there the modifications I've made to the program. So instead of requesting one number, I request two numbers, and then I've got to put a loop over the loop that I had. I have to put another loop so that I cycle through all the values of A. And I can modify further so that I then take the 10th number in the sequence. The reason I want to take the 10th number in the sequence is what I'm really interested in is what value is the sequence converging to. And let's move to okay, so this is the final one that I'm really interested in. So this time I'll run this program. So I've made further, I've kept making refinements to the program. So this time I'll actually start with the number 1 to A equals 100. And what it gives me are only the values of A for which the sequence converges to a whole number. And we can look at that in a spreadsheet, and then students can look at patterns. And then at the end, there are some questions, and you'll in fact realize that this relates to the golden rectangle. So you start off with a very simple activity, and as you go further into it, it has more and more levels of complexity that you can add. So that file is available there for you. I think it's all explained how I've gone from one program and added more features. So I would encourage people to have a look at it after the webinar. And I'm over time, so it's over to David.
Thank you, Frank. And like you said, Frank, I think that the first time you look at some of this stuff, it can be a bit daunting, and there's a lot to learn. As I was just talking to one of the attendees via Q&A, there's plenty of support out there, both in terms of the website, like you showed, and the e-guide that's available, and also even contacting TI themselves in Australia to actually get some advice from them. So there's plenty of support out there.
Yeah, absolutely. And I don't have any special skills, so I'm self-taught, just looking at those resources. If I can do it, I think anyone can do it.
Yeah. So, David, if you can now share your screen, please. We can then see your screen.
Okay.
And that's right. I think that sometimes, Frank, that they can see that we sort of, they think that we sort of, I don't know, I've learned everything sort of on overnight, but it takes us time as well, and we're all using it in the classroom with students, and just takes a bit of time to work through it. But like I said, with the support of all the online resources, it makes it a lot easier, doesn't it?
That's right. Absolutely.
Okay. Thank you, David. All over to you.
All right. Thank you, and good evening, everyone. Frank sort of finished with a confession. I'd like to start with a confession. I've done quite a lot of programming in various contexts, but certainly for writing programs for the classroom, in fact even back on the TI-83. However, I can't admit that I've used it in the classroom a lot, and I wondered, like Frank did, about are there other places around the world where they do use programming in maths as we seem to be being asked to do in our 7 to 10 curriculum. So at a recent conference I discovered that in France the use of algorithms and programming has now reached such a level that they include programs in senior maths high-stakes exams. So I wanted to start with, I was obviously interested in the sort of things that they do. I'll just show you a couple of examples. This is from the French system, but it's from the European Baccalaureate. And this is from a senior calculus-related exam, and I think you can see there, as part of that exam, they've got listed, even though it's in French, a little algorithm that's there that the students are being asked to interpret, to place a value in, and I think also to question the limits of such a program. So that's one example, and I'll just have time to show you another one. And it turned out that really every year's exam has at least one, sometimes two or three of these algorithms for students to deal with and to answer questions in response to. So we discovered subsequently that the use of programs is actually written into their middle school curriculum as well, and they are expected to write small programs and to make sense of small programs. So I do that now just to say that we're not alone. There's a number of other curriculums around the world that are doing this. So having discovered that, I thought, well, knowing my school, your school, if you had to try to introduce programming and coding and algorithmic thinking, what are the sort of ways that you might do it, and what sort of professional development might teachers need for that? So with that in mind, I tried to develop a single activity and try to think through what would be some of the issues for the students and the teachers that would be engaged in this, and what some of the background that they would need, and how much help would they need to be able to do it. So I think you can see this Hare and Tortoise task, which is based on a simulation of a race.
Yep.
And just because it's fun, I think I'm going to show you what it looks like. So the basic story in the race is that the hare and the tortoise are racing, and if you roll a die, a six-sided die, and the score is a 6, the hare advances 6 steps and wins the race. However, if you roll 1, 2, 3, 4 or 5, the tortoise will advance 1 step. And so the open question is how often, or proportionally how often would the tortoise win the race? So here's the fun bit. I've rolled a 2, so the tortoise is advanced 1. Then I roll again. Tortoise is doing pretty well. And you'd have to say there's a good chance that the tortoise will win. But in fact the hare wins and the tortoise is upset. So I think that gives you an idea of how the actual simulation works. But, and that's a list of the rules I think you can see there. And so initially, like many other simulations that we do, I guess this is sort of pitched more at year 9 and 10 when they're doing probability. And you might initially want them to just manually do it with a die in pairs, record the steps on something like a probability chart. And I'm not sure whether people have used these. If there are any older teachers in attending tonight, they'll remember that I think the DIME resources used to have these things called probability charts. And in this, John or Frank, can you remember this chart?
Yeah.
Yeah, so it's quite a nice style of thing that where you identify a win and a loss, and as a recording sheet, if they win, they move in one direction, and if they lose a particular trial or race in this case, they move in the other direction, and then it moves through the 50 trials and ends up in a sort of an overall approximate proportion of wins. So in this case, for example, this recording in the sample that's there, it looks like the tortoise has won slightly over 30% or 0.3 of the 50 races. Okay, so, and just as a matter of interest, I had a lot of trouble finding this. So I made an Excel spreadsheet which actually does this, and that'll be in the materials that you can get at the end if you want to source something like that. Okay, let's move on. So the next activity is to get the students to try to write a program that will simulate just a single race. And like Frank was saying, thinking about how do you make a program which just does something, the basics, and then stage 2 and stage 3 and whatever other stages might make the program more advanced by just doing more things for the right reasons. So initially we just want to get the students to write a program to simulate a single race and then report who won. They could record the results of these in a probability chart as well, or on the same probability chart. So this next screen shows you my thinking after having seen the French experience with the baccalaureate program, and speaking to one of the teachers that was involved in that, and she said that they commonly use flowcharts or pseudocode. So for those that aren't familiar with pseudocode, it's not specific to a particular programming language, but it's sort of a half English, half code interpretation of what's required for the program. So I think Frank used similar headings. So to simulate for a single race, there's some setting up of the variables and initializing them if you need to, and do here. And the main body of it is the algorithm, and then the third part is just to, like Frank was saying, cleaning up and displaying results. Now what I discovered from most of the French exams and from the textbooks I looked at French textbooks in maths, is that they had a very similar structure. That is, an initial setup, and then they talked about an algorithm, and then they talked about the sort of end thing where you might display results. So I've sort of borrowed from that and used that for this particular program. So without going into great detail, I tried to keep it as short and simple as I think it's possible. You've got to use a random integer generator, and then, like Frank's saying, you've got sequence of commands, you've got some selection or some decisions to make. In that case, there's there is a loop. There's a while loop as well. And so you repeat this trial. It's basically simulating the roll of the dice until one of them, either the tortoise or the hare, gets a value of 6. Now, you could use a number of different programming languages, but the one that we're using tonight is the TI-Nspire Basics. And on the right, you'll see some code which has been written as a program, Hare Tortoise 1. And I think you can see that that will do the same. I think Frank's shown you some of the commands that would be required. And I think that speaks for itself. And this is just a sample output from the program without actually going to it in great detail. And it just reports who won, the hare or the tortoise. So that's sort of level 1. And of course, in using a program like that, you have to be guided by what the experience level of the students are. But in writing it up as a task, I felt that you can't assume too much of the teacher or the student in terms of their programming background. So it's better when you're doing such a task to just include as much as you can to assist where necessary. Okay, so level 2, that program, is to say, well, wouldn't it be nice to do a number of races? And that's, of course, using the existing code and then adding things that allow you to do it for a number of races, where the user can enter the number of races they want to simulate. And then it would report the number of wins of the hare and the number that the tortoise made, and then the approximate proportions of wins for the tortoise. So, activity 2. So, same structure, some pseudocode on the left, and you'll notice there's a couple of more variables defined there for H wins, which is the hare wins, and T wins for the tortoise wins. And now there's a for loop, which is really saying the user's entered a number of races. We're going to simulate the race, and the code in the middle in that algorithm on the pseudocode is really very similar to the one which is used in activity 2. And the program on the right just lists how you would do that in TI-Nspire Basic. So what does it look like? It looks like this. You run hare tortoise 2, and you say that you would like to run that race 50 times, and it just reports back how many times the hare wins, how many times the tortoise wins, and then the proportion of that. So in the activity that you're doing with the students, of course, you're interested in what do they think. What do they think the long-run proportion might be? And so all the normal things that we would do in a maths classroom when we're doing such simulations before talking about the theoretical probability. But of course, that's sort of where we're going next. We want them to write a program to extend the one from activity 2 that runs the simulation for n races, records the list of the race numbers and the cumulative proportion of wins. By that I mean after the 30th race, it tells you what's the proportion of wins in those 30 races for the tortoise and for the hare. And at the end, report the wins and then report the approximate proportion. And the other good thing is that it generates a list which we can use to look at how the proportion changes as the number of trials increases, and that's sort of the next thing. So here's the code for that. You'll notice that it's certainly longer. It's not a great deal longer, but there's more things to define. And I think you recall earlier on Frank mentioned the Augment Command. Can you see that in the third line? Maybe my mouse can do it. But if you see on the right-hand side in the program, there's some lists that have been defined, one for the actual race number, so say 1 to 50 if we did 50 races, and then the current or the cumulative proportion of wins for each of the hare and the tortoise. Then inside the for loop there's now an augment thing, which Frank was explaining. It's really saying add something to a list, and that's really what it's doing. And then a lot of the code is the same for from activity 1 and activity 2. And the new thing is those two commands down the bottom where you're adding things to a list and storing the proportion of wins for the hare and the tortoise. So this is a very, I suppose, simple screen that's just saying, well, you run the program and here are a couple of the lists that have been generated. And you'll see that race list is really just recording the number of the race, and the tortoise win proportion list is just the cumulative or the changing proportion of wins for, in that case, the tortoise. So the cool thing is that you can then use that data, and you can ask the students to generate a plot using the output of the programs, and ask them what happens as you change the number of races from 50 to 100 to 1,000 to 5,000 to 10,000. Now, I tried it with 10,000, and on the computer, it really does work, but it seemed to take about 5 minutes. Mm-hmm. So you have to be careful how many trials you choose in terms of, it does work, it doesn't crash, it just takes quite a while. If you imagine it's running a lot of races, and each race isn't really short either. So this is some sample output from the program, and you can see that I'm sort of giving the game away. Maybe you can't see it very clearly on your screen, but the red is the proportion of the turtles winning, and the blue is the proportion of the hare winning, and they do seem to be converging. I've only tried it for 100 trials in that screen, but it certainly is there is some evidence that it's converging, and so we asked the students, is it possible that we could work out what those values would be?
The nice thing is, David, as well, is that they can go, like, it's a really nice progression, isn't it? You've gone from the practical aspect of actually, you could even do it with actual physical dice, to the online game situation, to think, well, a code's going to save you time. Even that nice probability chart that you used earlier, that replicates its sort of self in that graph as well, doesn't it? So students can see the importance of using code to speed up the longevity of what they're doing.
Yeah. So, I mean, this was the first time I've tried to write a classroom maths task and incorporated into it some coding, and I've really only just finished it, so I'm keen to try it in my Year 10 classroom, which I will be doing at the start of Term 3. So I will be able to report back on how it goes, and probably I'll refine it. One of the things I'm not sure of is how long it takes to do such a thing. But I am running a unit in second semester with a Year 10 class, which is called Algorithmic Thinking, and this is the sort of thing that we wanted to muck around with and try to learn about. Just to finish that task, to give the game away, this is sort of an illustration of the possibilities theoretically, and it should be no surprise if you do the maths for that it's really 5/6 to the power of 6, or about 0.3348997, which is the long-term probability that we're expecting it to converge to. So that's sort of the end of that task. And I have included, for anyone who's interested in trying it with their classes task write-up, as well as a few of the other resources that are needed. So I'm very happy and to hear about how you went with it as well. So that's the end of that task, and the only other thing that I would like to do is to say that I've seen a few other things, and sort of Frank alluded to this, but here's an example of another, I consider it almost to be a unit of work. I don't know if you can see that clearly. Can you see that, John?
Yeah, that's fine. Nicely zoomed in. Thank you.
One of the gurus of coding in the United States secondary maths classroom, he's been doing this for more than 20 years in his classes, was asked to write up a task, and he decided to use just the concept of divisibility and asked students to write programs that did a number of the tasks to do with divisors and whether something is prime. And you can see the time that he's got on the side there. And I think that depends on the experience level of the students, but I think that's the sort of thing that I'm going to try to approach next, to look at a sequence of programs that do sort of build on each other, that teach the students some of the underlying algorithms for divisibility, and to get to extend them to do it. So the last couple of things there about perfect numbers and amicable or friendly numbers aren't trivial to program, and I can see that that would be a pretty engaging sequence of tasks for students who are able to manage the coding aspects of it. So at 7:57, I think that's a good time to switch back to you, John, and thank you everyone for listening.
Thank you, David. That was great. And it's fantastic that those resources are available for us as teachers to use. So, yeah, thanks for making those available. And like I've said, and I'll talk again in a minute, they will be available on the on-demand and also in the email that gets sent out. I would just like to just mention a few things that were discussed earlier by both Frank and by Frank. Mainly is the webinars that you can go to. So I saw on the home page of the TI Australia website, and you can go to those webinars there. You've got the on-demand one, so you can watch the one tonight again if you want, if you missed something. So also here's the TI codes that Frank mentioned. And when we click on that, you've got the 84, the Inspire, and then now the TI Innovator Hub, which I would recommend you learning more about. If we go on to here, there's all the 10 minutes of code that you can do. So this is for the Inspire. And there's all the units already prepared for you that you can run through with your students, or they can run through themselves. And if you needed some support for that as well, either through the Teachers Lounge or here on TI Basics resource, you can actually get all the information you need through the e-guide of anything that you actually need. And that's all available to you as well. And that's loading, so there we go. Everything that the gentleman talked about tonight is covered in here. So plenty of support for you there. And we will now wrap things up. So thank you very much, Frank and David, for such an informative webinar and inspiring us all to try some different styles of codes. If you have any last-minute questions, please try and get those answered, or asked, I should say, and we'll answer them. And I know Frank and David will endeavour to give you some responses. Also, we can add those to our planning of future webinars. When you leave the webinar tonight, a brief survey will automatically appear here in your browser, and your feedback guides us as we plan future online events. We listen to your feedback, and so we hope you do share your thoughts in a post-webinar survey. Your certificate of attendance will be emailed to you in the next 48 hours, along with a link, as I already talked about, to the on-demand and the YouTube version of the recording, as well as any relevant documentation that both Frank and David talked about tonight. And if you do need some post-webinar follow-up, please feel free to phone or email us. We'd love to hear from you. And sadly, that brings us to the end of tonight's webinar. Thank you so much, Frank and David, for everything you've shared tonight. I really appreciate it.
Welcome.
Welcome. Pleasure.
And thanks everyone for joining us on a busy time of the year with reports and everything happening and the end of semester 1 getting near. So we hope to see you back online soon, and thank you very much indeed. Have a great night.